of this tutorial is going to be presented by Pierluigi Mancarella, who, if you were here from the beginning, you'll have met already. But as you can see from his title slide, he's got a split personality or something. He's at both the University of Melbourne in Australia and the University of Manchester in England. I suppose he has to go to Melbourne to get a dose of sunshine every now and again, since Manchester is one of the rainiest parts of Britain, and Britain is pretty rainy to start with. So, yeah, over to you, Pierluigi.
Thanks, Keith, and yeah, that was exactly the point. So what I'm going to do in the next 45 minutes is to talk about provision of grid flexibility from multi-energy systems, so a topic that has been touched upon already by you, Graham, and Alex, but try to be a little bit more specific in terms of definitions and modeling. So these are the overall topics I would like to cover, a little bit of background, and then how we move from power system flexibility to multi-energy system flexibility. Then some sort of modeling aspects and flexibility features, as you will see what it means exactly. And then some ideas, examples by some specific visualization that we developed recently. And then the role of networks in a multi-energy system, particularly in the context of flexibility, before, of course, the concluding remark. In terms of sorry, before I go into that, just as references, I will provide references slide by slide, basically. However, if you look into the overall narrative, this is basically taken from a recent paper that we published, which was basically a tutorial on multi-energy system flexibility we recently published in the Proceedings of JETRIPOLE. There was a special issue edited by Misha Cherkov and Gora Anderson. So the paper was actually very perfect time, I would say, for the paper given the topic of the tutorial. Now, a little bit of motivation, although has already been given largely, I would say, by the previous speakers. But I would like to give a little bit of a different perspective. Like if we look at the concept of flexibility and look at who provides flexibility today, and there's a sort of intuitive slide that I copied from Tomislav Sapodja from University of Zagreb. Anyway, I mean, the general idea is that you would provide flexibility either by flexible units, as you know, or would you import flexibility by interconnectors? Primarily, there are other ways of doing it, but these are really the primary ways. Now, what happens tomorrow when actually, for example, these conventional generators that are the current major providers of power system flexibility and services in general, we get out the market and to leave space to renewables that, at least in the current conditions, may not be able to provide similar services, and on the other hand, are requiring more and more flexibility themselves, given variability and partial uncertainty. So the overall picture of who provides flexibility, what kind of flexibility is required, is changing. And of course, one of the sort of responses to this is let's try to have more and more storage. And we look, for example, in Australia, but also in the UK and elsewhere, there's lots of interest in batteries. But of course, it's not only about balancing supply and demand, it's also how you do it and at what cost. So the idea is, can we look into flexibility from different sources? For example, can we look into flexibility that will be coming from heating, cooling, transport, future fuels like hydrogen in future, with the idea that when we do this, we will be able to access somehow different sources of flexibility that may be much cheaper than batteries or other similar technologies, and at the same time they allow us to decarbonize other energy sectors, as was introduced by Keith at the beginning. First, then, in this context, we just try to understand how we link the general flexibility concepts and requirements to multi-energy flexibility. Now, let's go with some definition. If we look at general terms, I mean, there are various ways you can define flexibility, but really to keep it simple would be the ability of a system to cope with events that may cause imbalances. And for example, for power system flexibility, looking particularly at sort of demand side, distributed energy resources and new technology are coming up in the system, I took a couple of definitions here again, one that I like particularly is from Ulrich, which is like very, very simple, straightforward. Technical ability to regulate the power exchange with the grid. Then there are other very well-known and important papers, like, for example, I took here a paper from 2015 by Makarov, where they introduced the so-called flexibility triad metrics, effectively looking at aspects such as ramp rate, power capacity, energy, particularly associated storage. They are all somehow defining different features of flexibility, which we will see later on. Now, how do we model this sort of power system flexibility before going to energy system flexibility? Again, I took this paper that I consider a milestone paper that looked into very simple, relatively simple modeling. It was called power node formulation. It basically looks at having sort of intermediate some kind of storage here, then energy inputs, energy outputs, energy losses, and then you can define in general some kind of energy balance that looks like this. This is not the original formulation, it's my reformulation of the formulation, because then, as you will see, this allows me to do some tricks when we get into the multi-energy space. However, basically, it's some kind of straightforward dynamic where you have the dynamics of energy storage. We'll see some capacity of energy storage. Here, this H is generally indicates some form of efficiency is associated with charge, or in case discharge, also depending on how you write the model, your storage. Then you have some net demand, because you may also have some local sources there. And then we indicated here with W some generation demand curtailment, because you may be sort of forced to do some curtailment, or this may actually be used to create flexibility. And then there is also some loss function. So effectively, this is a generic energy balance equation for a kind of storage system. However, you write it in such a way that you can identify, potentially highlight potentially the major sources of flexibility, including, in this particular case, dynamics of storage and generation demand curtailment, besides, of course, inputs that comes from the network. Now, once we said this, how do we extend this to multi-energy systems? And in this picture, I'm actually sort of highlighting what we call distributed multi-energy systems, particularly if you look at this kind of energy hubs that have been presented before, where effectively you can imagine you have all these aggregations of local energy systems where you have electricity, heat, cooling, gas, all the energy vectors that here are indicated with this nice colors, and then all these different hubs would interact with each other through these energy networks. So what is flexibility in a multi-energy system context? So in other words, how can we use other energy systems and vectors to provide power system flexibility? And another important question, can lack of flexibility in other energy systems constrain the electrical power system? Because it's not only we gain a source of flexibility. Given these tight interactions in the future, actually, we could also lose some flexibility because the other systems are lacking flexibility. So let's see how we could define this then, flexibility to power systems from multi-energy systems. An early definition was given by papers of a few years ago, where this was actually called electricity shifting potential, where effectively the definition was maximum reduction in the electricity input from the electricity system. So basically how you can, for example, reduce the input from the system in this case, which can be obtained starting from a given operational state of the multi-energy system. When you were doing this, of course, you will need to still consider the relevant multi-energy operational constraints in your model. So effectively say, how much can I shift the electricity input from one point to another, given that inside my plant, my energy hub, I can do different kind of tricks. Recently, there was an interesting paper, it was like 2019 by Hinke, that gave a very, very similar definition of operational flexibility, looking basically at the ability of modulate certain power feeding to the grid, or in case a feed out to the grid. But effectively the idea is how much can I modulate the electricity input given the source of flexibility I have internal to my energy hub, for example. If we want, we can actually be more general than that, because with these definitions, we focus only on the electricity vector in terms of what kind of flexibility we like to provide to the electricity system. Of course, that's the main focus. But in more general terms, we can say that this would be the ability to regulate the multi-energy supply, demand, and power flows subject to relevant constraints. So it's not only about regulating the electricity inputs, outputs. Potentially, you may also be interested in regulating the other inputs, outputs for the other energy vectors, so in a sort of true multi-energy context. Of course, when you do this, immediately you realize that you start discussing about multi-vector spaces, and therefore you need basically multi-dimensional arrays to deal with this. Whereas, for example, in the power node formulation, we basically had just one energy vector, and the equations were basically scalar and relatively straightforward. As a specific particular case of the general multi-energy flexibility definition, and of course, if you focus on one energy vector, and in particular onto the electricity energy vector, basically you fall back into the previous definition that were given for the electricity flexibility that was coming from multi-energy systems. However, it may be more general. I thought it would be good to point it out. Once we have defined this, then the idea would be, how do we actually build a model for this multi-energy flexibility? And we don't have to do too much work to start with, because fortunately, Gade and Anderson were doing this work for us about 15 years ago, as it was mentioned, when Martin Gade in his PhD thesis developed this theory of the energy hub, which is effectively linking a number of output energy vector V0 to a number of input energy vectors, so this is VO, the output, to input energy vectors VI. And then, of course, you may also have, in general, some energy storage, which here we indicated as E is the amount of energy stored, and E dot describes the dynamic of the energy storage. S is, again, a matrix. This is, of course, a matrix formulation, because there are multiple inputs, multiple outputs. And S is a generic storage matrix that is effectively describing the conversion efficiency and the losses of different storage devices. Now, this is the sort of underlying model of how you can relatively simply model the interaction of the energy vectors. How do we model the flexibility? Well, the idea is, again, let's try to generalize the simple power node formulation to having multiple energy vectors, and let's call this multi-energy node model, which effectively corresponds to this kind of formulation, where now you have basically a storage matrix. Here, this is like the dynamics of the energy content in your storage inside your hub. Then you have H, which is effectively the efficiency matrix that describes how the input energy vectors are interacting with the output energy vectors. Because in between there is also the dynamics of the storage. And then in this second equation here, what we did is we basically rewrote the output energy vector in such a way that they would look, again, similar to the power node formulation, so that we could highlight the kind of flexibility options that are available when I operate in this multi-energy space. Of course, you have some demand here, and this would be local demand that is being supplied by a renewable energy source. So effectively, this is a generation term. And then again, with the term W, we indicated general flexibility options that are coming from curtailment. VD would be curtailment of demand of edge vectors. VC would be curtailment in local generation, potentially from renewables. And then this VO is a sort of unique type of curtailment flexibility that is coming when you have different vectors are interacting for specific devices. For example, this is related to the possibility of being able to curtail heat when it's being produced by combined heat and power to, for example, supply some, to provide electricity without being linked necessarily to the heat that is being provided. So this is quite specific, and I would invite people to read the paper for more clarification. However, this general formulation here basically is written like this because it highlights effectively all the multi-energy system flexibility features that are generally available. And this is exactly what I'm going to do next. Basically, I'm going to illustrate how these equations here that are effectively like they're matrix equations because they interlink different energy vectors are going to be translated into sort of real world examples that we are quite familiar with. But when we look at this, let's try to get some more understanding. First of all, as we're saying, when you look at the power node formulation, so only electricity, that is effectively a single vector, scalar, and if you really want to keep it simple, so linear form, that in case it can be represented in closed form. So potentially what you can do is, if you want to analyze the flexibility that is coming with respect to the electricity grid, so basically how much you can modulate, for example, your electricity input into a certain system, you can basically write it still in closed form because you can basically sort of invert the system, which is scalar. When you have a multi-energy system, and this is the general formulation, however, you have now a matrix formulation, and H is the formulation, the fundamental matrix in the energy hub formulation that links the inputs and the outputs is generally non-invertible. So you can't really write in closed form a matrix expression that can explicitly represent in VI if we were interested in understanding the variations of VI, basically the deviations of the electricity input from a given operating point. This deviation then we would associate it with flexibility, as I'm going to show you in definitions in a couple of slides. So we immediately realized that actually moving from a single vector to multiple vectors starts becoming quite complicated because of the nature of the mathematics really that is involved in the very basic description of the modeling itself. I'm sure this is not coming as a surprise to anyone. So what we can do in general is to try to write just VI as a generic form like this, where what we do is to highlight effectively what are the main parameters that are playing a role, particularly in terms of flexibility. And here basically we wrote VI, which again is the term that we're most interested in because we're interested in understanding how much we can change these input vectors, particularly input electricity, by changing things. And here we wrote VI as a function, again, of H, so the matrix that connects the inputs and outputs, S, which is the storage matrix, and X, which is the array of the system control variables. And this array in general is basically VI itself, because you can control this, the input energy vectors in general. Then you have this delta that is so-called dispatch factors, which I will illustrate in a second. And then again, the energy storage content of different storage devices for different vectors. Could be thermal storage, could be electricity storage, could be hydrogen. And then again, V, that is the flexibility that is coming from various types of curtailment, which we will again discuss in detail soon. And now about these dispatch factors. What are these dispatch factors? Well, effectively, here, which represents sort of relatively complex multi-energy plant, multi-generation plant, we have electricity here, electricity network. The fuel network could be gas typically, and then you have a combined heat and power, an electric heat pump, an auxiliary boiler, and an absorption chiller. This is called water absorption refrigeration group. In fact, this is a chiller that is being supplied by heat and produce cooling. So when you look at this, effectively you have the electricity as an input, fuel, typically gas, as an input from your networks, and then you have refrigeration, so cooling energy, heat, the red one, and then of course electricity in green. As you can see, there are different ways inside the plant that you can actually supply the different components, but also finally the different energy vectors, electricity, heat and cooling to the users. Now, how you actually define, for example, how much fuel is going to the combined heat and power, how much fuel is going to the auxiliary boiler, how much heat is going to the user directly or to the absorption chiller and so on, depends on this kind of variables that we call here alpha, that basically indicates the split at sort of decision points within the hub to supply different devices. So this alpha here, this effectively control variables are what we called dispatch factors that really describe internally to the plant all the multiple paths that you have, and then by controlling the values, numerical values of these dispatch factors, actually you can basically determine if you want to use a path more than another. For example, you want to use this electricity from your combined heat and power to supply more directly your plant, sorry, your demand, or you want to use it more to supply, for example, your heat pump to produce heat or cooling, depending on what you need to do. This would be like reversible heat pump in this case. So already by looking at this, actually we started realizing that there is lots of flexibility in what we can do here, and in fact that was exactly the point that I'll show you in a second. Now, how do we define formally this flexibility after we mentioned a few times, but not really formally define it? Well, we can introduce a multi-energy flexibility array, we call phi in general. And then of course, we can talk about upward and downward flexibility. And we will associate this to the, basically to the set of all the feasible variation delta vi for each k, where k is each input energy vector. So basically, you may imagine that in here you have, in general, if you have, for example, electricity and gas as an input to your plant, in fact, in here you can have electricity and gas, and then you can define an upward flexibility for your electricity and gas, or a downward flexibility for your electricity and gas. So basically, you have a set of upward and downward flexibility. I'm stressing here on the term feasible because, of course, you can only change your inputs and outputs in both energy vectors, in this case electricity and gas, subject to all the other constraints that you have in your system, and particularly all the kind of constraints you have defined by basically your energy hub formulation. And then subject to potential flexibility variables that will be arising from decision variables that we described earlier. So this concept of feasibility is key actually to identify the possible variation in the energy inputs. And as I put here, these variations are subject to relevant multi-energy node constraints that we have introduced before. Focusing in particular on electrical flexibility, I really wanted to sort of be super precise. We could talk about both active and reactive power, but let's focus on the active power here. And finally, let's define the flexibility as effectively upward and downward variation on the on your active power coming as an input to your energy hub. Again, looking at the feasible deviation that you will have as a function of all the parameters and the variables that you can control here. And again, all of these somehow are subject to the multi-energy node constraints. So in other words, how much can I change upward and downward my electricity input while I consider all of the constraints that I have in my energy hub, and I consider all the flexibility that I have from the various control variables that depends on different features. What are these features? Well, first of all, we see immediately from this formulation here that the flexibility for one energy vector, and electricity in particular, is a function of all energy vectors, and they are linked by the multi-energy node equations. So immediately you realize mathematically that actually what I change in one vector depends, is tightly linked to what I can do with the other energy vectors. The multi-energy system then is inherently more flexible than the electricity-only system, because basically I have more control variables. So mathematically, as I was showing earlier in the example of the dispatch factors, I start having more parts effectively to, for example, supply demand, and naturally by controlling, for example, internally to the plant, the multiple parts I have to supply my multi-energy demand, I can also modulate the input energy vectors. Mathematically, this corresponds to having a certain number of degrees of freedom. These are effectively flexibility variables that I can define, so that the same operational point may be reached by multiple paths. And this is really like the key. There's also a very interesting paper that I would invite you to read by Wang and others from Professor Kang from Tsinghua University, Professor Kang's research team, where basically they developed, they show with the methodology how effectively you can have a linearized formulation of the energy hub, and then by looking at the matrix properties, particularly the ranks of matrices associated with the hub formulation, you can actually define some flexibility features in terms of degrees of freedom and all that, which I've just mentioned. So there is actually a mathematical way of describing this. I invite you to have a look at the paper. It's really interesting. This is effectively the one very basic feature of flexibility that is sort of relating to the ability of shifting energy vectors in input by playing with what I have inside my energy hub. And there was the idea, in fact, of the electricity shifting potential that I was mentioned earlier, that was a sort of early idea of multi-energy flexibility. Why did I say this is just the most basic? Because effectively there are many potential flexibility features that we could consider, particularly looking at input energy vector shifting arbitrage. So this is the electricity shifting potential. We also have output energy vector shifting arbitrage, this so-called power to X. Then we have temporal arbitrage by multi-energy storage. This is associated to the concept of virtual energy storage, again, many of us are familiar with. And then there are ideas about multi-energy service curtailment, for example, linking to comfort to power arbitrage, which I will show you in a second, relaxation of soft constraints, and then other aspects that are related to local curtailment, which I will skip for brevity. It would take probably too much time to comment on everything. However, I want just to try to highlight with some simple examples the fundamental features of this. So let's start with the input energy vector arbitrage. As I said, this is the fundamental flexibility feature. It can be exercised by changing the input energy vectors through modulation, for example, of the dispatch factors that are inside the plant in different ways. I have two types, effectively. One is external, the other one is internal to the multi-energy system. In one case, for example, I can switch between energy vectors. For example, I can use externally to the system, I can arbitrage between electricity and gas if I, for example, have a hybrid heat pump. And internally, I may have, for example, a complex system where I have, for example, combined heat and power, heat pumps, boilers, and all that. And I can, again, modulate internally all these dispatch factors just to change the allocation of one energy vectors to the different internal devices. Let me just give you an example, it'll be easier. So when I say external energy vector arbitrage, look at this. I basically have an electric heat pump and a boiler, and effectively I can decide, for example, not to use the electric heat pump to have electricity, but instead to use gas to provide heat. Effectively, this is the model of a hybrid heat pump with a sort of gas boiler top up that was also mentioned earlier by Keith. And in this case, basically, I shift, for example, from electricity to gas to supply my heat demand. This is the example of internal energy vector arbitrage, where effectively I have now multiple ways of providing heat by CHP, by heat pump, by boiler, and I can also use potentially different parts, because, for example, I can decide to use some of this electricity to be supplied to the heat pump to supply my heat demand, as opposed to having, for example, electricity going to as an output to my electricity system. So clearly here you shift the inputs, and here instead you sort of elaborate within your dispatch factors that are internal to the plant. However, as a final result, in both cases, you basically change the value of electricity that you are exchanging with the electricity grid. Why would you do this? Because, for example, if you have a system that is very, very peaky, like most of sort of European systems, like UK system, for example, by using gas boilers to cover the peaks, and basically by using these hybrid heat pumps, effectively you can get to saving something like, the system started with this some time ago, you can save about 20 gigawatts of electricity peaking investment, because basically you use this sort of flexibility options. What are the options do I have? Let's look at this multi-energy storage arbitrage. So in this case, effectively what I can do here, I can explore the opportunities that are coming from sort of intertemporal arbitrage in this case, and the features that belong to this case would be typically power to heat and virtual energy storage. How can I model this? Well, first of all, just by adding a thermal energy store here, immediately I decouple in time the electricity and heat supply and demand. So, of course, I introduce immediately a new form of flexibility that, although associated with heat, is of course allowing me to play a lot more with the electricity inputs and outputs potentially also. How about power to heat? Well, power to heat is this idea of using, in case excess electricity, to supply heat, whereby the heating system effectively works as some form of sink, and therefore is basically, again, a source of flexibility. And if I have thermal energy storage, of course, it's very beneficial, because, again, I can somehow decouple supply and demand when I do this. Can I generalize this to buildings? Yes, because as you would know, I can, many models that we have of buildings effectively are models of equivalent thermal energy storage. And effectively, if I substitute this thermal energy store here with a building, and then I describe the building with its multiple storage components that would be primarily coming from sort of thermal inertia in the building, again, I have an equivalent a thermal store, but in this case, it's the physics of the building that is providing that. This is the idea of virtual storage coming from buildings. In fact, this virtual storage really can operate as a virtual battery, as we will see. In fact, when I look at the with more insights into this, and I look also at these components of curtailing the energy services, I can see how effectively, once I am within my building, I can start playing with the content of heat I have in the building and the building thermal inertia, but also with the temperature that can modulate inside the building. Yes, I will lose some comfort level because, for example, I decide to switch off the heat pump and then the temperature will change within my building. However, I am now able to exploit additional flexibility that is coming from that. And in our formulation, this corresponds to some form of curtailment that we have introduced here in my demand of energy vector. In this case, it would be for heat. This is what we call comfort to power arbitrage and relies on virtual storage. Let me explain you better what this means. Look at this idea of virtual battery. I have a baseline. Suddenly I decide to switch off my heat pump, for example. So my demand goes down, for example, by 400 kilowatt for an hour. This is like real case from the UK, by the way, of some time ago. This effectively corresponds to, say, switching off demand to supply heat into my system, corresponds to discharging electricity into my system. Then I need to recover my energy later on. This is like sort of payback effect, because I want now to reestablish, after I switched off my heat pump, I switch it on again. I need to reestablish my temperature, and then usually I have sort of energy payback that is greater consumption than what the baseline would have been. And as you can see here, this effectively corresponds to some kind of charging my virtual battery. So here I'm discharging, here I'm charging. So as you can see, a building is not operating very differently from a battery, although the efficiency is quite different, because as you can see here, somehow what I charge is much less than what I discharge. So effectively, this kind of system will have a much higher efficiency than 100%. So where's the trick here? The trick is that in the meantime, I have actually lost temperature. So the thermodynamic boundary should also consider how much temperature I have lost. And that's why, in general, I talk about comfort to power arbitrage, because effectively I am sacrificing temperature, comfort level, to actually providing power flexibility. Now, how do I describe this? If I want to describe this from a sort of visualization perspective, how could I do this? Well, effectively, you could use some kind of what we call flexibility operational regions that have this kind of forms. Looking at a simple CSP example, for example, they can link heat and fuel, fuel and active power, heat and active power, and then reactive power and active power. So normally we used to, in power system, we look primarily at the interaction between active and reactive power. In this kind of systems, we'll be looking primarily, in these specific cases, at the interaction between, for example, heat and active power. Now, I have put here a number of examples in the next slides. However, basically, I would just mention the ideas, and then I invite you to sort of have a look later at the papers and at the slides with a little bit of easy, because I knew that I wouldn't be able to cover everything, but I thought it would be interesting to put it anyway, just to explain you the general aspects of that. Because effectively, the idea is, if you take all these different representation, where effectively you take in a 3D space, fuel, active power, and heat, and then you have, for example, linear representation of what combined heat and power is, a boiler is, electric heat pump is, power to gas, the plant is, thermal storage is. But when I look at this kind of representation, effectively, I can now create the picture of my energy hub by using Minkowski summation. So I start basically from this sort of very simple linear representation of these different components in these spaces. Then I adopt Minkowski summation, and I get this kind of plots that effectively describes how heat and fuels are linked to each other, how fuel and active power are linked to each other, how heat and active power are linked to each other for different kinds of combination of plants. And what is really interesting is that by combining different plants, effectively you have very different flexibility regions. Particularly if you focus on heat and active power, you see how different combination of plants give you different operating regions. Then if you start thinking that you can start, for example, mixing up further these power plants, then you realize that your flexibility really increases very, very substantially. That, for example, in a general case here, we put together combined heat and power, an auxiliary boiler, heat pump, and a power to gas plant. You will have here all of these linear representations that now that they are summed by Minkowski summation effectively corresponds to this polytope that when projected on the different planes gives you the flexibility maps of different energy vectors in pairs. And again, if we are maybe particularly interested in the active power and heat maps, you see that when you aggregate all the different technologies, the equivalent that you get, which is the gray region, is much, much larger than the sum of the individual aggregates. This is again the fundamental aspects of flexibility, that when you aggregate these different components with different energy vectors, basically the sum that you get in terms of operating region is much, much larger, and hence you create a much larger operating flexibility for your multi-energy hub. How about networks? What kind of role would networks play? Well, networks actually represent both enablers and constraints. Enablers because having a network allow you to, of course, aggregate. You cannot aggregate plants if they're not linked by networks. But the moment that you have constraints, they also actually limit the flexibility they can transfer across different systems. Again, this is intuitive because mathematically, obviously, this will correspond to have some form of linear constraints in your modeling. And then Alex was somehow showing effectively how you could use linear formulation to represent your network constraints. The most important thing is that mathematically, you cannot just apply this vanilla summation or Minkowski summations. Actually, you now really need to build this flexibility maps by multi-energy flow equations, the likes that Alex introduced before, and the likes that you will see with Misha and Vittorio this afternoon. And also, once you have this kind of networks and network constraints, effectively you start having segmented flexibility regions. And as I can show you here, for example, if you look at this very simple system with an auxiliary boiler in node A, an electric heat pump in node B, and you link these two systems with a heat network, depending on how large this heat network is, and if you look at the flexibility in the heat and power space, looking at node A in green and node B in purple, you see that the flexibilities in the two nodes change with the amount of, with how big basically this heat network is. And if you have no network, effectively, the two nodes are completely separated, the two regions are separated, there is effectively no flexibility available. And the moment that you have a heat network, you actually now create flexibility in active power too, up to having a heat network that can fully transfer heat between node A and node B, and you end up with basically the original flexibility map that you would have had with a Minkowski summation.
I mentioned, Pierluigi, you've got about, we've got to 1:45 now. We have got some interesting questions have come in as well. So yeah, it'd be good if we can leave some time for them.
I'll just go on 5 minutes, Keith, and then I'll.
No more than 5 minutes, please. Yes, right.
No, absolutely. Thank you. So yeah, similar aspects, of course, you understand now that this is just heat, but then if you start introducing gas, for example, you can start having, for example, power to gas. And then you start having more interesting questions like, for example, how can I combine, for example, the boiler, the heat pump, but also power to gas, and what is the role that the gas network is playing here. And here basically we show that depending on what network you use, for example, you use a heat network here, or use a gas network, or use both of them, again, you completely change the picture of the overall active power flexibility with respect to the heat flexibility. So having different technologies, including power to gas and different kind of multi-energy networks, completely changes the flexibility pictures of other energy vectors. And then the moment that you introduce constraints in those networks, again, you would change actually the amount of flexibility that you can derive, because effectively now these constraints are inhibiting and preventing from having the full flexibility. And then there are a couple of other examples that I will skip. But no, I think the sort of the idea is pretty much clear. Now, the last thing that I wanted to touch on is the idea of what can I do with networks and network flexibility. So how can I exploit network embedded storage that Alex was mentioned earlier, and that you will see later with Vittorio and Misha. So one idea is, again, the linepack flexibility. And you have to see Misha's presentation. It's got quite some details on this. So how can I play with gas pressures to actually derive storage and maybe useful for my electricity system. And again, for heat, look at Elisa and Vittorio's presentation. The other idea is hydrogen. How much hydrogen can I inject into the system, into a gas system to have flexibility in terms of power to gas. And as you mentioned earlier, the interesting thing is that when you start introducing hydrogen into your gas system in volume %, you will actually change the content of gas inside your system. And basically when you inject, for example, 20%, actually you will lose about 10% of energy content. This means that to actually carry the same amount of energy to the final user, by assuming that the energy you would like to use is still the same, actually you will need to have larger gas flows in your network. Therefore, actually you will need to run gas flow equations to really understand, once you have a mix of hydrogen and gas, if you're still within your gas network constraints. And you will see a little bit more details of this with Misha later on when we present gas networks. However, there are also benefits on doing this, because, for example, you could use this power to gas as to store electricity as some form of seasonal storage of your electricity that, for example, could be curtailed. However, you need to be careful, because the moment that you inject hydrogen to gas network, effectively you will change the properties of the gas system, and therefore you need to make sure that all the physics is still there. Just keep this. I just want to mention as final remarks that I hope it was clear somehow that this superior flexibility we hear very often coming from multi-energy systems, and also coming at relatively low cost, because we have lots of virtual storage and energy vectors, effectively is coming from this idea of having multiple parts and multiple control variables when I integrate different energy vectors. What I want to say is that we're really, however, only scratching the surface. I mean, when we start really talking about, for example, markets and full integrated network analysis, when we start talking about dynamic aspects of flexibility, here I only spoke about steady state aspects, effectively not how fast, for example, I can provide this flexibility. And when we start talking about planning for flexibility, the picture becomes much, much more complicated. And particularly when we look into planning, put here this, that when we want to plan for flexibility, well, you will need flexible planning methodologies. Because, for example, what we have shown in previous work and what we've seen done by others is that if you really want to exploit all the flexibility from all technologies in operation, you need to plan properly. But the moment that you plan under uncertainty, which is really what we're talking about in terms of planning, then you also need suitable planning methodology to develop this, and particularly linked to the kind of stochastic planning methodologies that would be really the backbone to develop future energy systems. Yeah, some acknowledgements. Don't miss this kind of sessions if you're still interested in power systems, multi-energy systems, and flexibility. And I will finish here. As I said, I thought I would add a little bit more content because I wanted the slides to be available, so you guys can go through at your pace. And then, of course, there are the papers, and please reach out for any questions. Thank you.
Great, thank you very much, Pierluigi. Yeah, so that's the general point actually about making the presentation slides available. So hopefully they will be available. You will have seen on the PACC program website, listing the kind of timings of the different sessions, and you've been able to click and see the abstracts. I think that's probably where we will put PDFs of the presentations. So we'll get around to that hopefully in the next couple of hours, and certainly by tomorrow they should all be there. Okay, so we've got like I say, a bunch of questions that I will try and pick up in some kind of reasonable order. So yeah, there's one about, okay, we've talked quite a bit about space heating in quite a few of the presentations this morning, so I guess there's a bit of a bias in terms of where the presenters are coming from. But Pierluigi, there are big questions about cooling as well, aren't there?
Yeah, cooling is straightforward. I put an example of tri-generation in a previous slide, electricity, heat and cooling. I show heating just because it's somehow simpler to show from a fundamental perspective the interaction between electricity and heating. Cooling can be treated in a similar way because, for example, you can just use a heat pump for cooling rather than heating, and all the general methodologies would still apply. If you start having tri-generation or more complex systems, again, all the methodology I showed for flexibility applies. And actually, if you look at many of the papers that are referenced, they're really looking to electricity, heat, and cooling. So the bias was more for me to keep it relatively simple rather than actually heating itself.
Yeah, I mean, another part of the question that was asked was to do with whether demand for space heating will decrease as the Earth warms up. Well,
not sure.
What we see is an average rise in temperature, but the weather effects are still, very significant. So you see definitely still big variability in weather. And those variabilities in weather just do depend on exactly where you are on the planet, kind of continental effects, how close you are to the sea, how the weather systems interact, all that kind of thing. So although, for example, I can speak about the UK, there may be, on average, a reduction in the demand for space heating. At particular times, there will be almost certainly at least the same as what we see now. So we still have these challenges to meet, I think. Anything to add there, Pierluigi?
Yeah, I think you're covering everything pretty much. I fully agree with you, Keith.
Yeah, now there was a question about trading of flexibilities that I think the person who asked the question thinks you've answered already, Pierluigi. Must have, by the time you came onto some later slides. So if that's okay,
absolutely.
I'll regard that as answered. And then, okay, there's some of them. Well, what's the objective function in some of the optimization that you've shown there, Pierluigi? Is it about minimization of cost or minimization of curtailment or maximization of welfare? Yeah,
so that's an interesting question again. So what I showed here is actually the sort of the underlying flexibility. So what I try to show is the sort of the modeling of flexibility itself, because we talk a lot about flexibility, multi-energy flexibility, but actually we don't say what it is, where it comes from, how we visualize and all that. So I really try to stress on this because I thought it was something interesting we don't see in the literature effectively. However, in practice, then you sort of exploit this flexibility by using these as sort of constraints in a sort of optimization problem, as is mentioned in the question. It can be any, and we've done lots of work in the different papers. Effectively, what matters is that once you're aware of what flexibility you have and how you can exploit it, how actually you can use it to achieve a certain objective. It can be energy minimization, for example, this idea of shifting from peak to off peak. You can do it in different ways. You can use virtual storage arbitrage, for example. You can use real arbitrage. There are different ways. You can look at welfare maximization when you look at this from a system perspective. So there are different ways of doing this. But effectively, that's really the objective function. What I'm showing is like, with the constraints that will be used in the optimization.
I mean, I think in practice at the moment, I mean, we touched on this a little bit earlier, and maybe we'll come back to it in the discussion at the end of the day, but in practice at the minute, I think a lot of the kind of coupling of the different subsystems, if you like, the different energy vectors happens through markets at the moment. I mean, it might not be very effective, or the coupling is not very strong, or it's very difficult for individual actors to see the coupling, but it already happens that there is an exercise of flexibility by, for example, aggregators that switch off the air conditioning in hotels as a way of earning money by using less electricity when the electricity price is high, and then there's a payback that you showed, Pierluigi, where then hopefully when you have to pay back and cool the buildings down again, you're getting that electricity at a cheaper price.
Yeah. There is I think actually the last question by Matt is very relevant. Why the MES operators? Yes, exactly. I think it's relatively, when you look at this flexibility idea, it's easier to show, say, I got my plant, I got my multi-energy hub and all that, and I am the local operator there, then it all belongs to me. I can actually use all these energy shifting properties for my own purposes. Or if I am an aggregator, again, as you were just mentioning, Keith, I can actually play, for example, with different plants, and then I can use all this kind of flexibility aggregation ideas to switch between one plant and the other. When you start talking at the system level, things are less easy. For example, if you look at this interaction between electricity and gas, and for example, looking at in the future when we start injecting hydrogen into the gas network, effectively say, how much hydrogen can I inject if hydrogen, for example, starts creating constraints to my gas network? So I will need to have a kind of interaction between the electricity system and the gas system, and the gas operator that somehow is checking gas network constraints and sends feedback back, for example, to the hydrogen plants that will be, or to the electrolyzer that will be injecting hydrogen, for example, into the gas system. Of course, these are all, it's hard, first of all, to model technically. I don't think this has really been done properly yet. And then, of course, when we start talking about markets, as Keith was mentioning, this is completely unexplored yet. And that's what I'm saying. We're really only scratching the surface.
Yeah, and a lot of those market issues, it seems to me, are a lot to do with arbitrage over time, as well as between vectors. So, your motivation is that you can, from a market perspective, you can save money by doing something now or doing something later, and then there's maybe a payback to take account of. So the dynamics come into it, especially when you're making use of storage that is leaky. And there, like you were saying, the models get especially difficult when you try to take account of the dynamics, and maybe you're trying to make use of some forecasting as well.
Absolutely. Again, because this was really sort of introductory, I just try to keep a sort of single snapshot problem. Effectively, when you start introducing dynamics, it becomes really complicated. But then we will see more with Misha and
yeah.
later about this.
So I'm conscious that we're getting towards the end of this session. There's another question then about FOR is a great way to think about multi-energy system flexibility. Are all points in the FOR admissible? And what about the optimal zones of operation based on costs or CO2? Just remind us what FOR stands for again.
Yeah, it's basically it's like flexibility operating regions. So effectively, this is good question, Mats, again. So effectively, again, I really only showed sort of technical aspects. Associated with this technical aspect, there would be cost functions, and effectively you could actually, as you're saying, using different colors for different cost zones, so to speak. We actually done this in different works, but again, just to keep it sort of simple. I only showed sort of technical aspects without getting into the economics. Are all these points admissible? No. Actually, the flexi operating region would change depending on the network constraints and the operating point. I sort of skipped one of the slides, but if you go through that, so there are also some interesting examples where you show that actually these regions may also be non-convex. The moment that you have integral constraints like switching on and off generators, for example. So actually these flexibility regions change with time, and then with time also you have the network constraints that change. So it becomes really an interesting problem.
The last question, which I don't think we're going to have a chance to answer now, since we've just reached the end of the time for this slot, but maybe we will come back to in the wrap up at the end of the day, was about uncertainty and how it gets transferred across the energy vectors, and even when you're exercising flexibility. But what will be the impact of uncertainty on reliability of supply? I mean, I think that's a big question in itself that does merit some extra attention.
Let's keep it for the afternoon. I think we should make a note of this. It's really interesting, and I got my very good view on this, so it will be interesting to hear.
Oh, a very good view, right? We'll see if everyone agrees it's a very good view.
Yeah, absolutely. That would be very interesting to hear others. Yep.
Okay. Great. So I think we should wrap up there. Thanks very much, Pierluigi. So you're going to be back this afternoon chairing the next two sessions.
Yep.
So there'll be one, we're going to have a 45-minute break now. So those of us in Europe are going to go off and have lunch. Everybody else, I guess, you'll find ways of occupying your time, I'm sure, and keeping yourself going. So we'll come back with part 4, which is about heat networks in particular. So Vittorio and Elisa will talk about that. And then after that, a session on natural gas network and system modeling. And as we just mentioned, there will be a last half hour of discussion where we'll try to sweep up some of these other questions and look towards the future, some of these research challenges. So yes, thanks very much. And we'll see you all again in just about 45 minutes.
Thank you.